Hello everyone, I'm Zhengbang Chen. In this video, I will present our work of symbolic verification of fuzzy natural models. This is joint work with my students, Siang Zhao and Zongyang Li, and also Professor Ji Wang in my university. So the concepts in human minds of things in the real world are often fuzzy, without precise boundaries and definitions. Assuming that we have a sand heap consisting of 1 million grains of sands. So if we take just 1 gram away, it's still a sand heap. We cannot determine how many grams we should take away to make the heap not a heap, because there's no clear boundary to determine how many sands can make up a sand heap. Obviously, the traditional mathematical logic theory does not apply for this situation. So fuzzy logic appears. It allows an intermediate value between 0 and 1 to represent the truth of falsehood of a proposition. So after several decades of development, fuzzy control have made great progress in both theory and technology, and also in applications. It has been widely applied in different areas of controlling and decision making. A fuzzy natural model consists 3 parts: fuzzification, inference, and defuzzification. The fuzzification function accepts a continuous value and maps it to input fuzzy set values. And each fuzzy set value is distinct value. Inference part consists logical rules that relate input fuzzy set values to output fuzzy set values. And these inference rules are interpretable. And the defuzzification function outputs a continuous value based on the output fuzzy set values. So here is an example for a fuzzy natural model, which is egg cooker. So the input is the weight of the egg, and the cooking time is the output. There are 2 kinds of fuzzy sets. One is for input, which indicates whether the egg is big or small, and also for the running time, which means the long running time or short running time. So if the egg is big, we need a long time for cooking, and if the egg is small, and we need a short time for cooking, which is specified by the inference rules. So long time is equal to big egg, and the short time is equal to small egg. So for example, if we assume that the input weight of the egg is 16 grams, so the degree of the 2 fuzzy sets corresponds to the 6 grams is 0.25 for small egg, and 0.75 for big egg. So basically, the 60 grams egg is bigger. Model computes the final output value by defuzzification functions. So output value can be computed use different fuzzification methods. Here we use centroid method, which computes the output value by the area values and the abscess values. According to the fuzzification function, the long time area is blue shadowed, and the showdown area is yellow shaded. We can compute the area values and the abscess values. For example, here, the area value of the short time, S short time, is 0.5675, and the abscess value is 4.3125. And finally, using the centroid method, the output value is around 4.8 minutes. So we need cook near 5 minutes for a 16 grams egg. So as we can see, the functions and the rules are very critical for the fuzzy logic models. How to ensure the correctness of fuzzy logic models is really challenging, and especially when the fuzzy logic models are applied in safety critical areas. So the theories and techniques for ensuring the correctness of fuzzy logic models are needed. Until now, as far as we know, there's no general automatic verification methods exist for fuzzy logic models, especially for some general properties. And our key observations of fuzzy logic models are as follows. First, intensive nonlinear floating point computations are inside the fuzzification and defuzzification functions, also the output computation methods. Second, there are low input related loops inside the programs that implement a fuzzy logic model. So there's only some branches caused by the inference rules inside the fuzzy logic models. So our key idea for verification is to consider a fuzzy logic model as a program and uses program verification techniques for verifying the critical properties for fuzzy logic models. For example, the pre-post conditions like properties. Considering the loop-free feature, we can apply symbolic execution to verify the fuzzy logic models. We can explore all the passes systematically and verify the assertions of the properties on each pass. Besides, we encode floating point variables as real numbers to tackle the problem of intensive floating point computations. So this is our framework. It accepts two inputs, a fuzzy logic model to be verified and the properties. The output of our framework are the verification results. It is verified to satisfy the properties or a counterexample exists. So the model's designer can use the counterexample to replay and fix the problem. Next, we explain the key components of our framework. The input model must contain information on falsification functions, inference rules, and defalsification functions. The properties should be relations between the model's input and the outputs, which can be specified as pre-post conditions. For example, the egg cooker needs to be at least satisfy the following property. When the egg is less than 16 grams and the cooking time should be less than 5 minutes. So the generator component is in charge of generating a target program that implements the model and converts the properties into assertions in the target program. The target program is Python code, and which is easy and simple to understand. So the environment models are running environment of target programs. Until now, our environment models support most representative functions. Besides, we also provide the support for all the logical operators of fuzzy inference rules. And the SMT solver component is also critical for our verification framework. And here we employ SMT solver derail, which supports many elementary functions that are frequently used in fuzzy logic models. And the symbolic executor implements dynamic symbolic execution. If all the passes are explored and the low counter example is found, the model is verified. Otherwise, we produce a counting example that is the input, which satisfies the precondition, but the output violates the post condition. The designers can check their model if a counter example is found and to fix the problem. Since there's no previous formal verification tool for fuzzy logic models on code level, the purpose of our evaluation is to evaluate the effectiveness and efficiency of our method. We use 12 models, which are collected from the existing fuzzy logic engines. And these models have different scales. And the scale depends on the number of inputs, outputs, and the rules. And the properties are written by us with respect to the functionality of fuzzy models. So this is the result of our evaluation. And our prototype can successfully verify all the models. The last two columns shows the number of passes and the verification time. We can see that the verification time heavily depends on the number of inputs and the rules because they result in more execution passes. For the last two models, whose scales are pretty large, and we need hours to finish the verification. So let me conclude. In this paper, we apply symbolic execution to verify fuzzy logic models. As far as we know, our framework is the first automatic verification framework of fuzzy logic models for general properties. And there are following aspects for the next step. First, we need to do more extensive evaluations on more fuzzy logic models. And then we can enhance our tool to make it more accessible for the designers of fuzzy logic models. And on the other side, we need to investigate the scalable verification method for the composite fuzzy logic models. And last, our framework is limited to continuous functions, which is also a challenge for our verification. So this is the end of my talk. Thank you very much. So if you have any questions, please contact me via this email.